Hello students, in today's video we'll be discussing some interesting tricks to know how to locate the position of element in periodic table. We know there are so many elements in the periodic table, each element being placed in different group and different period. But if I want to know the position of particular element in the whole periodic table, how can I do that? So for that, here I am giving you trick, and this question is an important question with respect to your board exam. Okay, let us see. I want to calculate, or I want to know the position of an element whose atomic number is 4. Now how do I know in which group and in which period this element will be placed? For that, first of all, I will find out its electronic configuration. So its electronic configuration is 2, 2. For finding out the number of period, so what is the trick? Number of shell equals to number of period. Remember this trick. So in the given example, how many shells exist? 2. And therefore this element exists in second period. Coming to group. To calculate the group, we have to see the number of electrons in the outermost shell. If this number is either 1 or 2, then I will write it here. Number of electron in the outermost shell. If it is 1 or 2, then the group number will be equal to number of valence electron. For example, in this case, in the outermost shell, valence electrons are 2, and therefore this element will be an element of second group. So the element with atomic number 4 belongs to second group and second period. But if the number of electron in the outermost shell they are greater than 1 or 2, then we have to add 10 to this number, and that will be equal to the number of group. For example, suppose I want to find out the element's position who has atomic number 10. So the very first step is I will calculate the electronic configuration, which is 2, 8. Just now I told you number of shell equals to number of period. So this element is an element of second period because there are only 2 shells. Now for calculating the group, I will see the number of electron in the outermost shell. In the outermost shell there are 8 electrons, so I have to add 10, and therefore this element is from 18th group. You can check these answers in your periodic table also, that whether this element with atomic number 10, it really exists in group number 18 or no. Actually this is neon. Neon is a noble gas. We know the noble gases, they exist in group 18. Let us have one more example. Suppose I want to know the position of an element with atomic number 15. Remember, always the first step is to calculate the electronic configuration. The electronic configuration will give you the whole idea. Now the period. There are 1, 2, 3, K, L and M. 3 shells in this, and therefore this element belongs to third period. Similarly, here it is K shell, L shell, and here it is also K shell and L shell. Okay, so there are 3 shells, and therefore the element with atomic number 15 belongs to third period. Now to find out the group. In the outermost shell there are 5 electrons, therefore I have to add 10, and this element will belong to group 15. So this will be the answer. So I hope this trick will work out for you people. We are going to discuss the most important topic of this chapter, that is trends in the modern periodic table. Basically here we will be discussing about the physical properties like atomic radii, tendency to lose electron or tendency to gain electron, valency, etc. So the first trend that we are going to discuss is valency. We will first learn the definition and then we will see how does it vary in a group and in a period. Any physical property, when we are discussing its trends in the modern periodic table, first we will discuss its definition or the introduction part and then its variation in the group and period. Okay, coming back to valency. What is valency? The number of valence electrons present in the outermost shell of an atom. Now, how do this valency varies in a group? As we move down the group, means what? When we move from top to bottom, like hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, all these are elements. These are of group 1. Okay, so as we move down the group, the valency of all elements in that group remains same. For example, just now here I have shown all the elements of group 1, they have valency 1. Similarly, all the elements of group 2, they have valency 2. So elements of a given group, they will show the same valency. Like group 15, their valency will be 5. Group 17, its valency will be 1. And group 18, all the elements of group 18, they show valency 0. Now, since all the elements of a given group show same valency and therefore their characteristics are also same, or I can say their chemical properties are same. It is because the chemical properties are decided by the number of the valence electron, and in a group they have the same number of valence electron and therefore it will show similar chemical property. One of the important give reason question. Now when we are writing the answer, the term as we move down the group, this term must be included in your explanation. Let us see how do the valency varies in a period. In a period we are moving from left to right. For example, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Here I have written from left to right, or we can say across a period. So period moves from left to right. Valency, if we consider its variation in a period, first of all valency increases, then decreases and ultimately becomes 0. For example, the valency of lithium is 1, beryllium 2, boron 3, carbon 4. Now it will start decreasing. Nitrogen valency 3, oxygen valency 2, fluorine valency 1 and neon's valency is 0. So this is how valency varies in a group as well as in a period. From this topic you can have lots of questions, you can have conceptual questions, you can have reasoning question, etc. So that was all about the variation of valency. We'll move on to second property, but remember we are discussing all physical properties. The next property is atomic radii or atomic size. We know atoms exist in the spherical form. Okay, so if you want to calculate the radii, how we'll calculate? Obviously we'll take the distance between the nucleus, which is the center of that sphere, till the outermost shell but of an isolated gaseous atom. if you are not writing special these terms in the definition, the whole definition will be considered as incomplete and you will not get the marks. So let us discuss how does atomic radii varies in a group. How do atomic radii changes in a group? Let us take the example of this one. First group like lithium, beryllium, it is a sodium, potassium, rubidium, cesium. So all these elements, these are from group 1. So here I have written the atomic radii of these elements. Lithium 152, sodium 186, potassium 231, rubidium 244, cesium 262, all in picometer. That means as we move down the group, always these words must be mentioned in your answer. Atomic radii increases. And the increase is also a consistent increase. The reason lies in its electronic configuration. Lithium has an electronic configuration 2,1, sodium 281, potassium 2881, so on. So as we move down the group, the very first factor, as you can see, the number of shell increases. Here only 2, 3, 4, 5, 6, so on. So the number of shell increases. As a result, the outermost shell moves away from the nucleus. So as a consequence, the atomic radii increases down the group, although Z effective or effective nuclear charge increases. Effective nuclear charge means the charge of the nucleus, the mass of the nucleus, although it increases, although the power of the nucleus increases, still the atomic radii will increase. Actually, as the nuclear charge increases, the power of the nucleus increases, it tries to pull the electron towards itself. But in case of group, what happens? The outermost shell moves away from the nucleus as there is increase in the number of shell. And therefore we say, although Z effective increases or ENC, effective nuclear charge increases, the atomic radii will also increase. Now let us discuss how atomic radii varies in a period. I have taken the example of second period. These are the elements of second period and their atomic radii are written here. We can see there is a decrease in atomic radii. So as we move from left to right in a period, the atomic radii decreases. Again, for knowing the reason, we'll try to know their electronic configuration. Lithium 2,1, beryllium 2,2, boron 2,3. Similarly, I have written the electronic configurations of other elements. Now, as you can see here, the number of shell do not increases. So the first factor is number of shell remains same. So the electron is added in the same shell. For example, here all these elements, they have only 2 shell, and whatever new electron is added, it is added in the second shell itself. This result in increase in effective nuclear charge. Since effective nuclear charge increases, the nucleus pulls the electron towards itself, and therefore atomic radii decreases. Now this whole concept is very important one, and a straightforward 3-mark question is asked based on this topic. Now remember, these points must be mentioned in your answer key, or these keywords must be written by you people in your board exam. The next property is metallic character. Now whether I use the word metallic character or I use the word tendency to lose electron, or whether I say electropositivity, all these means one and the same. Actually, metals, they have tendency to lose electron. And since they loses electron, they get converted to cation. And that is what we call as electropositivity. Here I would just like to tell you one very interesting fact about the cation. The cation, they are always smaller than their original atom. For example, sodium and sodium cation. Sodium cation will always have a smaller size as compared to sodium atom, because it will lose one electron and that shell will become less, and therefore it will be smaller than the parent atom. Okay, now we'll discuss how this varies in a group. Now in a group, as we move from top to bottom, or as we move downwards, the tendency to lose electron increases. Why tendency to lose electron increases? Because atomic size increases. Atomic size increases, so what will happen? The outermost shell, it will be quite away from the nucleus. There will be less impact of the nucleus on the outermost shell. Therefore, electron will be lost very easily. And hence, as we move top to bottom, or as we move towards down the group, the tendency to lose electron increases. Reason I have already explained, or I will say metallic character, it will increase down the group. Now if we see the variation in a period, as we move left to right, the tendency to lose electron decreases. Why? Because the atomic size decreases. Atomic size decreases, therefore the nucleus will hold the electron tightly, and metal will, or the element will not lose the electron easily. So as we move from left to right, the metallic character decreases, or I will say tendency to lose electron decreases, or electropositivity decreases. And therefore on the left side of periodic table, we have all metals, and on the right side of the periodic table, we have all non-metals. So metallic character decreases from left to right. The non-metallic character, or tendency to gain electron, or electronegativity, it is just opposite to that of metallic character. Non-metals, we know they gain electron, therefore they form anion, and we say non-metals are electronegative in nature. Again, one interesting thing about the anions, the size of the anion is larger than the original atom. For example, chlorine atom and chloride ion. So the chloride will be greater in size, larger in size than the chlorine atom. Now let us discuss how does the non-metallic character varies in a group. In a group, what happens as we move down the group? In a group, when we move down, or when we move from top to bottom, the atomic size increases. Already the outermost shell is away from the nucleus. Already the valence electron, they have least impact of nucleus on them. Nucleus tries to get the rid of those electron, and therefore tendency to lose electron decreases down the group. As a consequence, non-metallic character decreases or electronegativity decreases. On the other hand, in a period, as we move across a period, atomic size decreases. Since size decreases, the nucleus, it will attract electron towards itself, and therefore tendency to lose electron increases, or non-metallic character increases, or electronegativity increases. The last physical property is reactivity. For metals, the reactivity increases down the group, whereas for non-metals it is exactly reverse. For non-metals, reactivity increases across a period. So reactivity for metals across a period it will decrease, and for non-metals down the group it will decrease. Let us try to summarize the things, and this is an important trick to remember all these variation in a group or in a period. This arrow indicates for a period, and this arrow indicates for variation in group. So atomic size across a period it decreases. Atomic size down the group it increases. Valency across a period, first it will increase, then it will decrease. Whereas the valency as we move down the group, it remains same. Similarly, metallic character or electropositivity across the period, it will decrease. But as we move down the group, it will increase. Non-metallic character or electronegativity across the period, it will increase, and down the group it will decrease. So this was all about the variation of various trends in physical properties in modern periodic table. So this was the last part of the chapter, classification of the elements. With this we have completed chapter 5 of class 10th, and with this we have completed chemistry course. Based on today's video, here are some self-to-do questions for you people. Try to do it on your own. That's all for the day. Thanks for watching. Have a nice day.